Morning, Luca.
Ciao Veronica,
¿Qué tal?
bien. ¿Estás en el despacho?
Sí, today I'm in the office. Let's see how it works. Sometimes the internet is not as good here than at home. But you know, final day.
For the moment, the connection is working perfectly in any case.
Thanks. That's good to know. It's always stressful, no? When you teach this way.
Yes.
We've been a year doing that. You too, no? I guess
Yeah, I gave classes during September, from September to January, then I finished only in the first quadrimester, and it was completely virtual, except for the exams. So
Oh, that's good at least.
yeah,
We had this mixed format where half of the class here in Valencia were present and the other half were at home watching it, which
I
means double effort, no? You had to be doing both things at the same time.
yeah, definitely you have to do both things. Yeah,
But yeah, whatever. Few more months, right?
hopefully, hopefully for next September will be normal again.
Anyway, shall I share screen? The whole thing is good. Put this. Nice music. So you're monitoring both the chat in Zoom and the chat in YouTube. Huh?
Yeah, I'm looking
Make it
both.
work. Eh?
Yeah, I'm looking both of them to see if there are questions also in the chat in YouTube. But it's fine. It's not so much work. I have both of them in the same screen, so.
Oh, okay.
And every two screens, one for your lectures and the other one for the questions.
Are you also recording all this in this school?
It's automatically recorded in the YouTube channel.
Ah, cool. So whenever you do that, then it gets recorded. That's it. That's good.
Yeah, and there are no problems of space because in the Zoom, as we are recording also seminars and so on, the space is start arriving to the limit in which we have to start removing things. But in YouTube seems to be limited space, so
That's good.
yeah.
All right, I can start it using.
Sure. So it's your right. We can start if you want.
Sure.
Welcome everybody to this last theoretical lecture on Standard Model NX. Tomorrow, that is the last day of this topic, there will be the tutoring class, so don't forget at 10 for 1 hour. And after the class, there will be the visit to CERN, the virtual visit to CERN. But today, let's finish with the theoretical class of Standard Model. It is about its mechanism, if I'm correct.
Yeah.
So please, Veronica, go ahead.
Thanks. Okay, so today we are finishing our path that we started thinking about the standard model in a slightly different way from the usual, really focusing on symmetries and the importance of symmetries, which I think is important to realize that when you are given this as facts, as God given, let's say, this is the structure of the standard model, quarks, leptons, forces, and the Higgs. There is actually something more important and more fundamental behind. And since probably most of you are interested not so much in the successes of the standard model, but how is it so successful and how you can replicate this in your, let's say, model building or whatever you want to do next, I think it's good to see this success from the point of view of the mechanisms behind, what makes it so consistent. Okay, so we started by realizing that the symmetries of space-time actually dictated the type of fermionic degrees of freedom we can think of. We also, the properties of electromagnetism dictated as well how or what type of fermions we could consider. For example, we could consider left or right fermions, where now you know what left and right actually means, is under this double covering of the Lorentz group. But then we realized that these left and right fermions are related by parity, so any interaction that preserves parity requires fermions that are actually invariant under this substitution. And that's what leads to this structure of Dirac fermions, which again, it was introduced to you with these gamma matrices and so on. And just, again, that's something that happens. But it's not true. These gamma matrices, their form, the kinetic term, the mass term, everything is dictated by that symmetry, okay? And then I also told you that the only guys that can be a bit more interesting, let's say, from that point of view, are these neutral fermions of the standard model, these three. And these, for those, you have more possibilities because the electroweak interactions, the ones they do experience, they do not conserve parity. So you could have different treatments if you want of left and right-handed neutrinos. And then yesterday, we also went into, once you try to generalize the chiral or the symmetries of the fermion fields, the global symmetries of the fermion fields that lead to fermion number conservation and so on, to make it a phase that depends on space-time, we realize that the only way of doing this, the only way to actually assume that nature has this higher and more general symmetry is to introduce new degrees of freedom, and this precise form that these degrees of freedom of forces is introduced in the standard model. So in the adjoint representation, transforming as they should, and so on. And finally, today we are going to see the last missing piece in the standard model. You see, behind any of these columns, there are lots of symmetries and principles to make them consistent. Now we are finally moving on this column of the Higgs mechanism. Okay, so let's move there. And I'm again assuming this is a doctoral school. I assume you have gone through some courses, the advanced courses of non-relativistic quantum field theory or field theory or whatever. And you're probably familiar, since you are in this school, already with the existence of the Higgs, and probably heard or learned about the Higgs mechanism in some way. You know about how the Higgs gets above and interesting things happen. So what I want to give you is, again, a slightly different view, a higher level view that helps you understanding more deeply the standard model, these mechanisms of electroweak symmetry wave. So we are going to first understand or discuss why we need this Higgs and why this mechanism is so highly non-trivial. So let's go back to what we were discussing yesterday. We have fermions. We know that fermions have a U1 symmetry or invariance in their Dirac equation. We try to make this is a global symmetry. We try to make it local. And that tells us that we should introduce gauge bosons. And these gauge bosons have to have a very particular transformation property, right? Something like some constant times some derivative of that phase that depends on space and time. Only in this case, only for fields that satisfy this kind of transformation, then the whole Lagrangian involving fermions and gauge bosons is invariant under this local gauge symmetry, okay? And then I told you that once you impose this, or you assume this, that you have this kind of transformation, then the kinetic term for the gauge field is settled. It has to be this F mu nu that you already know. I also told you that for non-abelian symmetries, the F mu is slightly different. It has this interaction term that you probably know about already. So I'm assuming that you probably know a lot about this, and it's just seeing it from another point of view. Okay, so here we are. Yesterday we finished saying that forces are just a manifestation. They are not something that we try to describe because we see it. Now we have to change our point of view. Now forces are a manifestation of a higher symmetry in nature, a local symmetry. The only way to, or what happens is that we want to do this higher symmetry, the forces are a manifestation of that. It's not, the story goes the other way, starting from a higher abstract or concept, which is a principle, a symmetry in this case, then you actually discover that there should be new degrees of freedom. And to make them consistent with this new principle, you get a very, very predictive framework, which is this theory of forces as gauge fields. When it comes to non-abelian the non-abelian case, for example, for the SU2 and the SU3 case for the standard model, the theory is slightly more complicated, and it took some time in the 50s. Jan Mills had to, work hard on making this consistent, these non-abelian gauge theories consistent with this kind of description. But they did it. Okay, so here we are. We are at this point where we have been able to move from space-time symmetries to internal global symmetries to internal local symmetries, and the discovery that forces are just a manifestation of that new type of symmetry. So this missing piece of the standard model, the Higgs mechanism, tries to answer a problem that appeared then. Okay, so I'm telling you that this local symmetry tells you that there should be a new degree of freedom, that it should actually change in a very particular way, and it should lead to this particular kinetic term. And this gauge symmetry does not allow the presence of, for example, a mass term for your gauge boson. This is something that you can write down. You can write a Lagrangian term that represents a massive gauge boson propagating. That would be consistent with SO31, because you see, this is a 4-vector and these indices are contracted. But it would not be consistent with the local symmetry. Okay, but you know that symmetries in nature are rarely exactly realized. When we think on our Lagrangian and we think that it has a symmetry, like yesterday when we were talking about the nucleon and the pions, we said, well, if the neutron and the proton have the same mass, is equal 0 in this case, then there is a symmetry, right? And this not only a symmetry, but a combination of symmetries. There's isospin and the baryon number. But what if the neutron and the proton don't have the same mass, which is actually the case? Well, then we say that what we can do is to think on this Lagrangian as being mostly symmetric and thinking on additional small pieces of these interactions of this Lagrangian that corresponds to the symmetry breaking. So often in nature, more often than not, symmetries are approximate. And what it means is that in your theory, there are some terms that break this symmetry, but they are small. So that means that the symmetry breaking terms are small, and small means as compared with other parameters or similar dimensions in our Lagrangian. All right, so typically when you're thinking about global symmetries, these global symmetries are going to find a way of being broken down in some way, even if it's very tiny. What about local symmetries? Can we afford having a local symmetry broken by a small parameter? For example, can we afford to have this master? The issue is that for gauge symmetries, because they are on a higher level kind of symmetry with respect to global, being more, having more structure makes them more and more stringent. And in particular, for for gauge symmetries, breaking down them explicitly, even if it's a small explicit breaking, even if it's a very, very, very tiny mass term for the photon, this is going to break, or to I shouldn't say screw up, but mess up the properties of your theories. So what is this problem? The problem is that you know that what we want to do is to compute physical quantities, a scattering, a decay constant, a mass term, whatever. Those are physical quantities. And what we know in quantum field theory, in the theory that we need to use, these physical quantities, typically you will compute them as some classical contribution plus some quantum contribution. For example, if you are thinking in terms of a Lagrangian, your Lagrangian may have parameters that are what you will call tree or bear, whatever name you use, parameters, and you will compute quantum corrections to actually understand in this Lagrangian what are the actual physical parameters. For example, thinking on the mass, or let's say the mass of my electron, this represents how this guy is propagating in space-time. It represents the propagator of this guy. And we can have a Lagrangian where we put ME as a term there. And that will be our bare mass. But we also have to consider possible quantum corrections. And these quantum corrections in a perturbative theory, well, there will be loops. For example, there could be a loop of an electron that gets, this photon and this other guy, and then you compute these kind of corrections. And then you do 2 loops, 3 loops, 4 loops. If the theory is perturbative, these quantum corrections are actually computed explicitly by taking more and more higher loops. But the overall propagation of the particle, what we see physically, is the addition of classical tree bear with the quantum corrections. So to have a predictive, to be able to give any kind of predictions, we should be able to compute of course, given some classical parameters, to compute the quantum corrections. So a predictive theory is a theory that is quantum and that where you can actually compute these quantum corrections. This is all obvious, but it will become important right now. Okay, so what people realized is that after Jan Mills, is that you could indeed write down a theory that, for example, had an SU2 local symmetry or gauge symmetry. This theory had this kinetic term and so on, but if you wrote down this mass term, which you were allowed to do, you could do, for example, this kind of mass term for, say, your SU2 interactions. That mass term was messing up the whole renormalizability of your theory. You were not able to write down a finite amount of counter terms, if you want in technical terms, for your theory. So writing down this mass term, no matter how small it is going to screw up this renormalizability of your theory. In other words, if you write down this mass term as it is, as an explicit breaking of your SU2 symmetry, no matter how small, you are going to not be able to produce physical predictions. So, and it was technically, back then, it was a matter of you started writing down counter terms and then you realized that you had to add more and more and more, and the series never stopped. So after the initial, wow, that's fantastic, we have a theory for non-abelian interactions, we can understand, for example, the behavior of W's and Z bosons and so on, they realized that accounting for a physical observation, which is the mass of the Z boson and the mass of the W boson are non-zero. One is 91 GeV, so it's really non-zero, and the other is 80.4 GeV. These masses, just writing them down and trying to describe them from a quantum point of view, from a physical point of view, it was not possible. So even back then, something happened that is very common these days as well. Is okay, so people said, okay, fine. So I write a quantum theory and I cannot, because there are so many terms that go out of control. So what I'm going to do, one guy came, I think it was called Feinberg in 58 or something, like very early on. He said, okay, so I'm going to write this master, I'm going to write the theory, the quantum theory, and I'm going to assume that there are specific counterterms which are exactly canceling with each other. So if I, also what Feinberg said, if I assume a very, very precise fine-tuning between different counterterms, then the renormalizability of my theory is recovered. But that requires an ad hoc fine-tuning, which was more and more severe, the more and more you try to actually reach more and more precision, so going to higher loop level. And this, you see, technically, this could be done. This will render the theory predictive again, but at the cost of a lot of fine-tuning, and ad hoc fine-tuning. So see here, this guy says, okay, I can solve the problem, but you need to assume a lot of stuff, fine-tunings, very specific fine-tunings. And you know, the Nobel Prize winners and the people that discovered the way electroweak symmetry breaking actually happens, that the Higgs mechanism actually does, is to explain how this fine-tuning is actually not a fine-tuning, is a consequence of a symmetry principle again. Okay, so that's what I'm going to tell you right now. And I wanted to mention this, let's say, trial by Feinberg, because that's a typical situation that happens nowadays. When you do model building, you're going to find that your theory is inconsistent unless you make some assumptions. And these assumptions are often in the context of some kind of fine-tuning. And what I would like to tell you, since you are going to be working on beyond the standard model, is that I believe fine-tunings are new principles waiting to be discovered. And one has to work harder at finding them. Okay? Fine-tunings are just indications, temporary indications that something deeper is happening behind. So, again, I'm assuming that probably most of you went through some course where they tell you, this is the Lagrangian of the Higgs, this is what it does, and so on. So I'm going to give you, again, a higher level view of why the Higgs mechanism works, and then we will see how it works. Okay, so the issue of renormalizability came from trying to add an explicit mass term, right? You try to add this in your Lagrangian, and then renormalizability breaks down. So predictivity breaks down. But think that renormalizability of a theory is something that has to do with the ultraviolet structure of your theory. When you compute loops, what you are doing, for example, over here in this loop I just mentioned, that corrects the mass of the electron, this loop, the behavior, what you actually need to renormalize often, has to do with the ultraviolet structure, with the fact that you can produce these particles in the loop virtually, so you can produce effects at high momentum, much higher than the mass of the electron. Okay, so in the case of electroweak symmetry breaking, in the case of trying to explain the mass of a gauge boson, the problem of renormalizability had to do with the ultraviolet structure of your theory. So the inconsistency came when you try to obtain predictions accounting for virtual corrections at high momentum. So all what the Higgs mechanism is going to do is going to provide a way of producing a mass term that it only depends on infrared corrections, and that it disappears as we go to the UV. All this Higgs, what it does, gets away, whatever, gets to the vacuum, all this stuff, is in fact the reason why it does solve the problem that we have is because the contributions to the master, to the propagation of the gauge bosons that come from this master are such that they are completely infrared dominated. So it's low energy and not high energy. Okay, I want you to keep that in mind because that's key. And for example, when you think again in your BSM models, this is the key structure that you need to keep into account. The Higgs, yes, does the work. The Higgs is the simplest thing you can do to achieve that. But there are more than one way of doing this. In superconductivity, for example, or in what in the past was called Technicolor, or the composite Higgs ideas, they all solve this issue, making exactly the same kind of mechanism. A mechanism where this mass, the mass that is screwing up renormalizability, is infrared dependent only. And the ultraviolet is not important. It's like if you want a master that at high energies, it dissolves and is no longer there. So there is a recovery of the symmetry at high energies. A very good, maybe a bit old, but a very good intuition and description of what I'm just saying right now is in this book of Coleman, or these lectures of Sidney Coleman that I gave you at the beginning. There's a chapter called Secret, or he talks about this secret renormalizability. And that's precisely the idea of Coleman, is that you look at the low energy theory, you look at the W's, the Z bosons, and this theory is not renormalizable, but it's secretly renormalizable because this master at high energies, it has a structure that is more symmetric. And that higher symmetry, the fact that at high energies, this master disappears, if you want, it's no longer there and playing a role, makes it, for this theory, to recover its renormalizability, its predictivity. Okay? So the Higgs mechanism is one way of doing this. It's apparently the simplest way because that's what the nature has chosen for the standard model. But it's not the only way, and it's something that you can keep into account when you think on possibilities beyond the standard model. Okay? And I don't know if you have any questions so far.
If you want, yes, there is a non-renormalizable imply infinity number of counterterms.
Yes, exactly, that's the thing. Yeah.
That is the only question that has been done up to now.
Okay.
There's another one, maybe. Could you please again explain why the mass is considered as an infrared dependence and not the problem of UV departure?
So this mass term here, the writing down the explicit mass term for your gauge boson, when you then analyze the structure of your theory at the quantum level, you had to start computing loops, right? So let's think about loops and not counterterms, just because you might be more familiar with this. So what you see is that having explicit mass term in your Lagrangian and then computing quantum corrections makes this theory non-renormalizable. If you have been given or gone through a quantum field theory course, and you have renormalization, for example, QED or whatever, for a theory to be renormalizable, it has to satisfy a set of conditions. In particular, you think about counterterms, is that for a mass term, for the gauge interaction, for every term that you have at the classical level, the quantum correction, the counterterm, the number of those guys have to be finite. And when you add this mass term, this is no longer the case. If you want, the technical description and how to see that, you can go to this Coleman book. And if you don't find the book in your library or whatever, please send me an email and I can send you a scan of this book. Okay, it's really, really good. So there was an issue. It's like, wow, the people back then were freaking out after getting, a fantastic theory for young beings that describes the things properly. Then at the same time, they realized that quantum theory is there, quantum field theory is there, that you need to normalize this in order to get physical predictions. And that particular theory is not possible to renormalize it. But this lack of renormalizability had to do with this mass term when you consider it at high energies with the UV structure. What if this mass term did not exist at high energies? Then the problem will be gone. So the idea of the standard model of the Higgs mechanism is to provide a way of, in a very subtle way, we will see in a second, it will provide a mass term that at high energies is not there, so that we don't have an issue with renormalizability. We can renormalize the standard model. We can get the predictions of the standard model with massive gauge bosons, because their mass is a term that doesn't come like this. It actually comes from an interaction with the Higgs, and only when the Higgs gets a vacuum expectation value. I'm going to explain all this in a second as well. But since I am aware that many of you probably already saw this, I want to give you a higher level view first, and to tell you that that is the key. You need whatever is modifying the propagation of the W and Z bosons, let it be an infrared effect, and then you'll be all right. And there are more than one way of doing this. The Higgs mechanism is one, but there are others. Okay, so in the last hour of this course, we are going to do the description of the Higgs mechanism, but also going step by step, going from a very simple global symmetry breaking. So we are going to talk about how we, having a symmetry, we go and break it with the help of scalar fields. Scalar fields are the only ones that can give us or have the ability of breaking these symmetries in that way. Okay, so I'm going to explain all this, but I'm going to do it in steps. We are going to start with a global symmetry, and a very simple one, just as the two, a parity, like we were discussing for that matter. Then we will do a global continuous, just a U1. And then I will move into a gauge, U1, which will be like the abelian Higgs mechanism. And then the generalization to SU2 is I wouldn't say it's straightforward, but it's just a generalization of this that you probably learned in your courses already. Okay? So let's start with the global Z2. So now, right now, we have done fermions, we have done gauge bosons, and now we are going to do scalars. And what scalars are able to do. So let's consider first a real scalar. Let's write the Lagrangian of this real scalar. It has to be something that has propagation of the scalar, d mu phi square, that's my kinetic term, that's T, and then minus V. This scalar could have a potential. And this potential can be the mass term for this scalar, and we can also introduce some form of interactions of the scalar. And you can put some numbers here, it doesn't matter, it's just a normalization. Essentially, this term over here is simply, if we have the scalar, this is dictating how this scalar propagates, or the part of the propagator that goes as 1 over p squared, and this other part over here, this mass term, dictates how it propagates, how this mass is changing its propagation, and this last term of the potential is simply describing possible interactions of the scalar. Okay, so This is very typical. Is the starting point resembles a lot what the Higgs does, right? I'm really sure that most of you already know what the Higgs mechanism is, and you know that is the lambda 5-4 theory. But here we are considering something much simpler. We are considering a scalar field that is real, and it has a mass term, and it has some interactions. That's all. So let's start thinking about this theory. This theory, with this Lagrangian, mu phi squared minus the potential, of phi, has symmetries, right? For example, we know that if I do psi, or the scalar field goes to minus phi, because all the terms in phi are quadratic, like here it appears twice, in the potential it appears twice, or to the fourth. When I take this Lagrangian and I substitute phi by minus phi, the Lagrangian remains the same. So this change of sign is a symmetry of my Lagrangian. Okay, and this is this two symmetry we were discussing in this real and complex plane is the simplest of these symmetries, 1 or minus 1. So now we are going to try to describe the vacuum of this theory, or the low energy description of this theory. We have a scalar, it has a Z2 symmetry. For the moment, it's just this. So we are going to analyze the maxima and minima of this potential. So we take first the derivative of the potential with respect to the scalar field. This is the kind of term 4 over 4, doesn't matter this much. And because we are trying to find extrema of this, we set it to 0. And now to know if it's a minimum or a maximum, we need to take the second derivative with respect to the field, right? And this goes as m squared plus 4 times 3, 5 squared. And whether this is positive or negative, it tells us whether we have a minimum or maximum. Now, remember that the Lagrangian is nothing but code for the action, right? The action is simply the integral over all the space-time of the Lagrangian. So when we consider all of the Lagrangian, or the symmetries that the Lagrangian says, is because we want to find also the ones of the action. And we know that the action is this guy that needs to be minimized, right? And that will lead to the equations of motion. Okay, so we need to find when we have potential like this one, what is the minimum? And typically, the minimum of this action corresponds to the situation where the Lagrangian, if it depends on fields, the minimum will correspond to setting all these fields to 0. And that's our starting point. That's like the minimum energy type of situation. And that's what you will do generally in a quantum field theory up to this point. Okay, so let's see if this is true. We know that this is true for fermions and gauge bosons. What happens for a scalar where we know the potential is a bit more interesting? For example, it has this lambda 5-4. Okay, so if we look at these conditions, we have this equation and this equation. So we realize that if the mass square, this mass term that I put there, the tree level, the Bayer mass is bigger than 0, then the only way we can reach that minimum is that phi itself is 0. So for this mass square positive, the vacuum of my theory, meaning the minimum energy situation of my theory, is that the field is 0. What is the meaning of that? What it means is that when we do quantum field theory, when we do anything really, like what we do is, if there is some distribution of my field, in whatever space, what I know is that the classical situation is going to be the situation where the energy is minimum. And my quantum field theory, my creation and annihilation operators and so on, what generates new particles and dynamics and so on, are actually perturbations around this minimum. So in order to do any quantum field theory, I first need to determine where is the vacuum of my theory. And then interactions and everything I want to describe will be applying annihilation and creation operators on those guys. But first I need to understand this. And typically this zero, this vacuum of my theory is a vacuum where nothing is present, where no field has any kind of value. So this is the typical situation you will expect. Okay, but what if m squared was less than 0? In that case, we could find two additional possibilities for minimum for the vacuum of my theory, which are, let me call it plus or minus some constant value, minus 6m squared over lambda. And if m squared is less than 0, these are the minima, and actually phi naught equals 0 is a maximum of my potential. So we examine the possible vacuum properties of this theory with very simple scalar field. We notice that it has a Z2, that's it. And then we realize there are two distinct properties or possibilities. One, if this parameter that we put in the Lagrangian is positive, we just get one single minimum. If the parameter is negative, then two more possibilities appears because this is now a real value. Okay, so we see that there are like two branches of possibilities here. Let's see what this means. So the minimum, again, of my potential determines what is the structure of my vacuum. And we now see that there are two possibilities. Let's start by plotting, if you want, what is this potential as a function of the field itself. What we see is that this potential that has this form as a function of the field, think on this as now a coordinate, is m squared phi squared plus lambda phi to the fourth with some power law here, doesn't matter, is that for m squared positive, for this parameter positive, we get just this situation. This is the potential we get. It has a single minimum here at phi equals 0. So the equation the minimization we just saw, this is a graphical representation of that. There is only one minimum. And what it means is that our quantum field theory, there is where the vacuum will be. So in the vacuum, we should consider phi equals 0 and then start moving up or down in energy. But if m squared is negative, something funny happens. The potential changes shape. Now here I want you to not get confused with you have seen probably lectures about the Higgs mechanism. Here, this is not the Higgs mechanism. This is not at the bottom of a bottle or anything. This is really just one dimension. Here is just one dimension. Okay? So if m squared is negative, the potential changes type of form. And then we see indeed that there are two minima that appear. Right? The phi plus and phi minus. Okay, so you see that we have then two possibilities for my vacuum. For starting to do my quantum field theory, I could choose this vacuum here or this other vacuum here. And these two vacua are different. Right? In these two vacua, the field acquires a different value, phi plus or phi minus. Hence, these theories are going to be different. Okay? So anything that we think of in quantum field theory, particles, interactions, scattering, comes from building a quantum field theory that starts with a vacuum and where we create and annihilate states. So the structure of this vacuum is important. Up to the Higgs mechanism, you didn't care so much about the structure of this vacuum because it was a trivial one. It was always at the level of the vacuum structure, the fields were all set to 0. That was the minimum energy configuration. But here, that's not going to be the case. Actually, we discovered that for that value of my mass parameter, for this being negative, a more interesting structure appears. So now when I want to actually look at my Lagrangian, that depends on my field. The Lagrangian, I know what it is the Lagrangian I had before in terms of that field. But if I want to think on or make it more manifest what the real physics is going to be, it better be that I think on perturbations around that minimum. So the Lagrangian that I wrote at the beginning, that's the Lagrangian of the theory. But when I'm thinking about, for example, expanding a quantum field theory here, let me call it 1, or a quantum field theory here, let me call it 2, these two quantum field theories will be better represented by thinking on the field as being the starting point, plus or minus, or the other way around, the actual propagating or interacting fields. So we want to start with the field. This is the original field. We want to actually shift it, that value, phi plus, and then think on perturbations, the phi tilde are going to be around that one. Okay? So I want to rewrite my original Lagrangian, change coordinates if you want, so that now it becomes apparent and clear who are the propagating degrees of freedom and where is a simple shift in my energy. So let's do that. We are going to introduce this shift. So we go from the potential that we have of 5 to another potential that depends on the actual propagating degrees of freedom. And then we are going to reevaluate the conditions of minimum on that vacuum. Let's do that. Okay. So if I do this, I get a V of 5, this potential. The kinetic term is trivial because just a constant shift, it stays exactly the same. So I don't even write it. So let's write the potential, which is the one that does a nicer thing. So I get 1/2 m squared 5 plus minus square plus lambda over 4 blah blah plus or minus to the 4th plus lambda 5 plus. Let me just write it down and then I explain to you what this is about. Plus 1/2 minus 2m squared 5 tilde squared. So the only thing I've done is to change from the phi I had initially to a new phi tilde minus 5 plus or minus. So that now it becomes apparent where is a constant. This is just a constant. And where is actually a propagating degree of freedom, something that actually carries the information of the physics. Okay, so what you can see here is that this is a constant. This is a constant, right? So these two terms are a constant shift of my potential. In classical mechanics, you've been told energies are defined, you are the one that defines what is the zero value for an energy, so a constant value in a potential is not important, and you can actually redefine it the way you want. In quantum field theory, that's a bit trickier. As you know, you probably heard about the cosmological constant and how it's not so highly trivial to do that. But let's say, for the point of view of this discussion, this is simply a constant, And it does not change the dynamics, at least of doing quantum field theory and of doing scattering and understanding interactions. So what we end up with is a theory that now has a propagating degree of freedom, phi tilde, with a mass term. This is the physical mass of my propagating degree of freedom. And you see that we are assuming that m squared, the three-level mass term, the classical mass term that you put was negative. This, at first sight, will look like, oh my God, you're adding a tachyonic degree of freedom or something. That's not true. Indeed, in the vacuum of that theory, it is consistent to set this value or this parameter m squared negative because the actual mass term of your propagating degree of freedom is positive, as it should. But then, now I have this mass term, so my phi tilde propagates as it should, no problem. It's not a tachyon, nothing worrisome with it. But now, instead of just having a quartic interaction, phi tilde cube, I also get, so this is the quartic, I also get a cubic interaction, something that goes as phi cube with a constant value here. Cool. So we've changed the way we look at the potential by explicitly expanding over the minimum, so that phi tilde is really the propagating degree of freedom, is really it carries the dynamics of our theory. So we are accounting for the non-trivial structure of our vacuum by simply doing that shift. The consequences of this shift is an additional contribution to a constant, that we realize that the propagating degree of freedom is non-tachyonic, as it should, but also that now, apart from these kind of interactions, we find new interactions that are proportional to this phi plus minus, this value over here, this constant. So, fine, so now our theory looks different. It has more types of interactions, and the field we have to account for, the one that where we are going to write a propagator, this is slightly different. Another thing is happening here, which is in this new theory, with this new potential, well, remember, it's just the potential you had before, where you have actually just changed coordinates. From the point of view of phi tilde, the symmetry is Z2, so phi tilde goes to minus phi tilde, is no longer there. This cubic term is not symmetric under the change of phi tilde goes to minus phi tilde. It picks up a sign. So this new potential, which is the old potential in terms of new coordinates, does not exhibit this symmetry.
Veronica, question.
Yeah.
Okay. So what about the linear term that would arise from the quadratic and the quartic term, and the quadratic term that would arise from the quartic?
They vanish.
Okay, very good.
Good. If you think that phi plus minus is a specific value that depends on the mass and the particle, it just vanishes. Good. Very good question. Okay, so where are we? We started with a theory with a symmetry, Z2. Then we realized that in order to do a quantum field theory, we had to start from the minimum of that theory, but it doesn't have one minimum at zero, it actually has two, plus or minus. So whenever I choose to start with phi plus or start with phi minus, obviously, well. So if I start to do a quantum field theory over here, or start doing one over here, those two choices are not Z2 invariant. The theory is still Z2 symmetric because my potential is Z2 symmetric, my Lagrangian is Z2 symmetric. But since the vacuum is not trivial. Yeah, the choice that you had to make of a vacuum to describe your theory, to do quantum field theory, breaks this symmetry. Now, this breaking is different from if I had at the beginning written down my potential, where I had, for example, mass terms, and I had lambda 5 to the fourth. If I had written some, let's say, lambda cube, something like this, that term will be explicit breaking of my symmetry. That will be explicit, because I explicitly write down my potential with a term that breaks the two. But I didn't do that. I didn't write that term. I just wrote lambda 5 to the fourth. And it's only after I do this shift, after I account for the vacuum structure of my theory, that this symmetry is not apparent anymore, that there is a breaking of this two symmetry. That type of breaking that only appears after you account for the structure of the vacuum is called spontaneous breaking. Here is, we can go back to this story about the mass of the David-Ansel boson. Realize that this is happening because we are actually looking at very small perturbations around the minimum, very low energies, or starting from the minimum, we just do a quantum field theory around that minimum. If we now think about perturbations that are high energy, so this is the potential, or you want the energy, and this is the field. If we now think about perturbations that are at very high energy, things that are happening up here, from this high level, this separation between phi plus and phi minus is not that important. And from that point of view, at very high energies, at least intuitively, you can see that that is not going to be relevant. So the source of this spontaneous breaking, this breaking of the Z2 symmetry, has to do with the vacuum structure. The vacuum is an inherently infrared quantity, meaning it's a low energy quantity. It has to do with the minimum energy that you can achieve. So the ultraviolet structure of this theory is not going to be changed. So spontaneous breaking of symmetries will preserve the ultraviolet structure of these theories. If they have good properties, they will stay there because the spontaneous breaking is inherently infrared. Okay? So let's move on then into a new, or let's, before we move on into a new, this global U1, we went from discrete Z2, we are going to go to another global symmetry U1. Let me just give you an immediate application of this Z2 and its breaking. You have then a potential, you have a scalar field that is real, and it possesses a Z2 symmetry. If the mass term that you write down is negative, then this guy is going to develop a non-trivial vacuum structure with two possibilities, right, that are completely equivalent, right? I could have started by phi plus or phi minus. They actually have exactly the same energy. So it's a choice, no? I could do one or the other. What I know is that this choice is breaking spontaneously the Z2 symmetry. Now, you might be wondering, okay, it's a choice, but what determines that choice? Who makes that choice? Where do we see that choice being made? So in these areas of new physics, sometimes you consider these kind of situations, especially for the early universe, where what will happen is that you have, let's say, a scalar somewhere at high energies that has this symmetry with this kind of properties and so on. You will expect that as you go from high energies or high temperature or early universe, you go down to low energies or temperature or so on. At some point, this potential is going to go from this structure where it has only one minimum to developing this more interesting structure where it has two possibilities. So what happens at that point? Think that the universe is evolving, is getting bigger and lowering its temperature, energy is in general going down. So it goes from a situation where this scalar has only one option, which is have zero value everywhere, to a lower energy, a situation where the scalar has to choose, quote unquote, right? I'm not anthropomorphizing it, has to choose between 5 plus or 5 minus. How in practice that happens is that as you think on the structure of space-time and you see how we are going down in energy, at some point, regions of the space may start evolving into developing the 5 plus minimum or the 5 minus minimum, and the 5 minus minimum, 5 plus. Different regions will start cooling down, and then this scalar is going to move in this direction or in this direction in its parameter space. Depending on whether it goes to the left or to the right, regions of the parameter space, regions of the universe are going to start being described by a vacuum that is 5 plus and 5 minus. Now we know that these theories are different, right? They are different. They have a different value for the scalar field. So as it keeps evolving, the 5 minus with the 5 minus regions will start merging with each other, creating a larger region with 5 minuses. Same for 5 plus, no? So what happens when then you have a region with 5 plus and 5 minus, and where the vacuum is that one, that vacuum choice, and that vacuum choice. Here again is space-time. We are think on a space, like it's really a space. What happens here? These guys cannot merge into each other, like meaning they cannot homogenize to have the same minimum. They are different minimum. They are distinct, this one and this one. So what is going to happen is that in the middle, something is going to appear, or the description of this boundary between the two vacua is going to become a domain wall, which is a structure, topological structure that describes the separation that exists between these two minima. Domain walls, or this is in the regime of topological defects. Sorry, I write it horribly. Topological defects are a set of possibilities that appear that describe these intermediate regions between the different vacua. Domain walls are what you will get for a Z2 symmetry. For other kinds of symmetry, you could get strings or more interesting types of topological defects. What we know is that cosmologically something must have, if there were any domain walls or strings or whatever in the early universe, if there were such situations being generated, these domain walls must have disappeared in some way. They must have decayed or done something interesting. So there is an area of beyond the standard model precisely trying to see the effect of domain walls, for example, in the cosmic microwave background, what happens there in inflation, and so on. That's all I wanted to say about the Z2. I'm going to then trivially go into a U1 global, and we are going to see there are a few differences. Okay, so we've done the simple real scalar. Let's do a complex scalar. So a complex scalar now is 5, and whereas the real scalar is one function of space-time, a complex scalar is two functions of space-time, the real part and the imaginary part, you could think of. Or if you want the phase and the absolute value. You can parameterize this complex scalar the way you want. Okay, since it's complex, now when we write the Lagrangian, it's going to be slightly different. It will have this derivative mu, right? But now to make everything consistent, so that my Lagrangian is real because it's all the physical parameters are real, I need to put a complex conjugate here. And when I talk about the potential, my potential also has to be real. So one way of doing this, one choice, what if the potential that depends on my complex scalar only depends on the absolute value? That will ensure that this guy is actually real. But let's do that. So I can, for example, write down that the potential goes as the mass term, so phi complex conjugate, and some lambda phi to the fourth. Those are choices. Okay. So we seen that before, to understand what's going on with the former theory, to understand that there was a Z2 symmetry and it was breaking down was interesting. Here, we are going to also have a symmetry. For example, this Lagrangian, if I now do phi complex guy goes to some phase times the same complex guy, because every time I write some field, I write the complex conjugate, obviously this Lagrangian is going to be invariant under this symmetry or this transformation of my fields. This is a global U1. It's global because I'm just considering alpha being a constant. Why? Because if I have a derivative mu here, I cannot consider so far an alpha not being a constant. Okay, so I do that. Then things become a bit more interesting, and to, for example, to represent this potential of phi, it's not enough to just write 5. I need to separate between, for example, the real part and the imaginary part of phi. Same story as before. You see, it's very, very similar to the Z2, except that now we have a function that is 2 degrees of freedom, this real and imaginary. So we had to think on this as a 3-dimensional space, right? For m squared, this parameter positive, this is the kind of potential we get. And now for m squared negative, we get this bottom of a bottle kind of potential. Sorry, I'm not very good at drawing, but hopefully you know what I'm doing over here. Okay. So we get the same structure as before, but now with a one more dimension. And same story, the solutions, when I do derivative respect to the field and second derivative respect to the field, and I evaluate these two conditions, is that if m squared is positive, there is only one solution, which is the whole field is 0. But if m squared is negative, which is this situation over here, then I get a more highly or a non-trivial solution, which is that in that, with m squared negative, there are solutions, the new vacua are going to be the values of the field whose absolute value is precisely this minus m squared over 2 lambda. Okay? And that is not one single condition or two conditions as before. It's actually a whole range of conditions that corresponds to the bottom of this potential over here. I'm sure that now it's sounding a lot more like the Higgs mechanism, because that's indeed the simplest potential you can write down. Okay, so same story as before. Let me define this V over 2 just for convenience. And what we are going to do is to say, well, now if I want to describe the quantum field theory of this Lagrangian, where m squared negative, I need to account for that I had to make choices about what is my vacuum. And now, instead of being 2, I have a continuous set of choices. Anywhere I write here, I decide to start and then do my transformations, do my quantum field theory, is going to be equivalent. And it has to be as good as a theory as anyone else. So as before, we are going to redefine our field, initial field, as having some phase, just to account for the fact that it's a complex scalar, the value of at 0, let's say we are taking off the original, so the value over here, and then we are going to redefine or show explicitly the 2 degrees of freedom of my scale, of my complex scalar. Okay, so what I've done here is simply write that I'm going to go from my field to the propagating degree of freedom minus the minimum. This part is the minimum, and this is my propagating degree of freedom. And the only thing I've done here is to write explicitly what is going to be the real part of it and the imaginary part of it. So H and chi are real fields. Okay, so if we do that, then we need to consider then the Lagrangian goes as, instead of depending on phi, they are going to depend on H and chi as propagating degrees of freedom. And the way this Lagrangian looks like, let me just write down on another page, is if we substitute, we are going to get the following. We get Lagrangian kinetic term for my Higgs, no, it's not for my Higgs, for the real part, kinetic term for the imaginary part. Then I get a term that goes as H times VQ lambda plus M squared V. I get then another term that looks as H squared, some constants. Then I get another term. I'm writing them explicitly because I want to explain each of them slowly. Half lambda V squared. And then I get interactions like this one. Plus 1/2 m squared v squared plus lambda over 4 v to the 4. Okay, so if you take the original Lagrangian and rewrite it the way I said, with this just field reparametrizations, what you're going to get is all these terms. This is simply just do the expansion. So what you get here is a kinetic term for a real scalar field. This is the kinetic term for the real scalar field. You see, even the normalization is the correct one and so on, the canonically normalized. Then you get a term that is constants times h. Whereas the kinetic term, we know what it is. For example, that would be my h or my chi that propagates. As for what this is describing, it has 2 fields and it has this momentum dependence. What is the interpretation of this field? It's like I have an H and then nothing happens. Right? It's a linear term in a field. That is called a tadpole. If you have a tadpole in your theory, redefine your field so the tadpole disappears, because this is not a physical condition. When you have a tadpole, a term like this one that is linear in your theory, it's because you are not using the right description of your theory. So here we get a tadpole. But actually, if you look at this and this one, what is the value of V, this vanishes. Okay, so this tadpole is not there. We don't need to worry about this tadpole. Then we get something that is again a mass term for my Higgs field. And although we know that the mass square is negative in our case, surprise, surprise, this mass square for my H particle is actually positive. So this is negative, but the physical mass term is positive as it should. So of course this guy is non-tachyonic. Then we get to the imaginary part, we get this mass term, which will be again chi goes to chi with some mass dependence, but this particular combination vanishes. So the mass term for my chi is equal 0. And then we get interactions that are of the type that are quartic, that we have also some cubic interactions, right? So interactions of this type or this type with chi's and h's and so on. And then we get these constants as before, which again will contribute to the cosmological constant, and we tend to neglect when we do quantum field theory. Okay? So we take our theory of a complex scalar. We realize that there is a symmetry, this U1 symmetry. We look at the structure of the vacuum, and it has emits a non-trivial structure with an infinite amount of degenerate possible vacua. We expand in any of these vacua, and what we get is that the end-up theory, the theory that is you want the low energies, what you see is a massive degree of freedom, a much less degree of freedom, and some interactions among these guys. That's all what is left. Okay, so we started with a U1 global symmetry. Any choice we make in this range of potentials, any choice is going to break this U1 global spontaneously. This breaking leads to a separation in U1 between the degrees of freedom of my scalar field. So I had 2 degrees of freedom at the beginning, with that corresponding to a mass term m squared. And after the spontaneous breaking of this symmetry, I end up with 1 degree of freedom that is a massive scalar, and 1 degree of freedom that stays massless. This is the degree of freedom that is called, this one, a Goldstone boson. There is this Goldstone theorem. I'm not going to describe the Goldstone theorem over here. Simply I'm introducing this theorem as a generic description of what we are seeing here. What Goldstone said is that if you have any global, and this is important, symmetry that is spontaneously broken, that leads to a low energy set of predictions, which is the existence of massless scalars, and these massless scalars are called Goldstone bosons. For each generator of this global symmetry that is broken, you are going to get 1 massless scalar. So if you, instead of U1, which has 1 generator, you break SU2 or SU3 or a larger group, instead of 1 Goldstone boson, in our case, this chi, you are going to get more Goldstone bosons. And this is unavoidable. If you are considering a global symmetry that breaks spontaneously because of the structure of this vacuum, that breaking leads to a very neat and clear consequence at low energies, is that you should expect massless degrees of freedom. The opposite is also true. We can take this now Goldstone theorem and what we just seen to say the following. So if I look at my theory, or I look at nature, and I see that there are sectors in nature where I see scalars that are very light, almost massless. The presence of these very light scalars is probably the consequence of a global symmetry that has been broken down. So this Goldstone theorem is behind the nature of these pions we were talking about yesterday. I told you that in the low energy sector of QCD, we had, the baryons, protons, neutrons, we have lots of mesons and baryons generated by these quark-antiquark interactions, but then we also get very much separated from the rest of the spectrum, these pions that are very light. So their origin can be traced back to the Goldstone theorem. When strong interactions confine, global symmetries of SU3 color. In this case, the flavor symmetries we were talking about yesterday, the SU and F flavor symmetries of the quarks are global symmetries. The strong interactions and confining break them down spontaneously, and as a consequence of this breaking, you get lots of Goldstone bosons, the pions. Now, Goldstone said that these scalars had to be massless. So if the breaking is of a global symmetry, then you get massless degrees of freedom. But actually, if this global symmetry is not exact, but is approximate, as it happens in QCD, this global symmetry, SUNF, is not exact because the quarks do have masses. Okay, they are very small, but they do have masses. So it's a source of explicit breaking. Then this global symmetry is not exact, it's approximate. So these massless scalars, the pions, then become no massless, but very light. And these Goldstone bosons, then they are called pseudo-Goldstone bosons. And again, as yesterday, when we were talking about nucleons and pions, if you start your analysis with an exact symmetry, you can always introduce the breaking, the explicit breaking later on. So the lightness of pions is due to their tracing back to a global symmetry that is only approximate. And the mass of the pions is actually related, or is related to the explicit breaking of this global symmetry, which is the mass of the quarks. Okay. And in the last 10 minutes of the class, I'm going to do again the not trivial, but the step of going from, we did Z2, we did U1 global, now we are going to do U1 gauge. What happens in this case?
Veronica, a couple of questions. So before you were speaking about the different bubbles that can be formed in the universe, in the case of the Z2, there are two questions related to this. So which is the dynamics between these two type of bubbles, for example? Are there tunneling effects?
Yes, very good. Excellent question. Yes. So if you think about the vacuum structure, we have regions in space-time that are living in this 5+, and regions that where the field gets this vacuum expectation 5-. So the region in between, so anything to propagate from one to the other, to move or interact from one to the other, has to actually either jump, let's say the quantum field theory that is able to go from one region of the space-time to another region is something at high energies, or as the student says, through tunneling. And the dynamics of these domain walls are indeed, because they are dynamics at low energies, we are talking about the expanding universe, nothing too high energy. It's through the tunneling processes over there. So to, for example, compute where is the energy stored in these domain walls and how much energy is going to be released when they decay, this is precisely through this tunneling computation.
And is there any dynamics that determine the appearance of the different type of webs, regions of the webs?
It's a completely random kind of process, right? So you have your action. I told you that the possibilities realized in nature are the ones that minimize this. Both of them are equally, probable, right? They are both have the same low energy or energy, the same value of the action. So it's a completely random process.
Okay, the last question on this topic. Are there formation of these bubbles even in the continuous case, or only in the discrete case?
In the continuous case, it can happen as well. It's just in the discrete case, we know the topological structure. Topological simply means that is something that extends in space and time. Usually when you think on quantum field theory, you're thinking on fields that are very local, right? You are thinking about local properties. Now I'm telling you that this non-trivial structure of the vacuum, this plus and phi minus, generates regions in space-time, whole regions extended in space-time that carry some properties. So the adequate description of these objects that are extended in space-time, that are infrared in nature, are precisely what is called a topological structure. So I am just mentioning Z2 as leading to domain walls, but there are, you can think on higher dimensional situations as well.
Okay, and the last question was in pseudo-Gospel bosons. Why the approximate global symmetry produce pseudo-Gospel boson, not just Gospel bosons?
Okay. So the Goldstone theorem and the prediction that there will be the appearance of new degrees of freedom that are exactly massless, that's obtained when this global symmetry is exact. If it's exact, exact, and it breaks down spontaneously, Goldstone theorem applies. That's it. But as usual, you obtain a prediction and then you start messing around with it. That's what we do all the time. We know that symmetries in nature tend to be non-exact, only approximate. So how do we modify the Goldstone theorem predictions when the symmetry is only approximate? So what is going to happen is that it will move from being massless gauge bosons, massless, massless scalars, to not being massless, but being quite light. Their mass for these pions, we know that if there was no source of symmetry breaking, their mass will be 0. If MQ is equal to 0, so what we know is that the mass of the pions must be a function of MQ, a function that when MQ goes to 0, the mass goes to 0. And as we were saying yesterday with the nucleons and the pions, these interactions, we say that, for example, the conservation of that current, those currents, was going to be proportional to the difference between these two masses. Because we know that when this is 0, then the current is conserved. And that the fact that we know that it has to be proportional to this mass difference is important to produce or to predict the effect of this non-zero mass difference. Here is the same. So we rarely we are going to find a situation with a global symmetry is absolutely preserved. It's usually approximate, but that doesn't prevent you from getting lots of good consequences from that. And the theory of pions is actually a theory of pseudo-Goldstone bosons, pseudo because they are not exactly Goldstone bosons, and whose mass is not 0, but is proportional to the mass of the quarks, to the explicit breaking of the global symmetry.
And the very last question, the effective breaking, does it change the nature of the Goldstone boson, for example, the CP nature, for example?
Yes, that's totally correct, indeed. So how this flavor symmetry, the thing that in the case of QCD, the flavor symmetry, the properties of QCD interactions and so on do play a role. The CP properties of the pions depend on what they are made of. And in particular, they will be there for the pions at gamma 5 playing some role and making these pions to be CP odd particles, as we were saying yesterday.
Yeah, yes, but independently of having a mass or not.
Independently of having a mass or not,
yeah,
indeed.
That was the
okay.
Okay.
Just to tell you that Goldstone bosons can be CP odd, CP even, can be whatever. It doesn't have to be the case that they are CP odd. There is no need. Axions and pseudo-Goldstone bosons, and they are also CP odd. But composite Higgses are pseudo-Goldstone bosons, and they are CP even. So it doesn't have to be a CP odd state.
Very good.
Very good.
Thank you.
Shall we move into the last part? Finally, we get into the Higgs mechanism. And the Higgs mechanism is this process of spontaneous breaking, now not of a global symmetry, but of a gauge symmetry. And as you can imagine, this will produce slightly different consequences. A gauge symmetry is more restricted than a global symmetry. There are a lot more in play. So let's see what this is doing. Okay, so we are going to consider a simplified version of the overall Higgs mechanism, but it captures everything that you need to know about the Higgs mechanism. We are going to take scalar QED, meaning we are going to consider a U1 gauge and a scalar field that is charged under this theory. So we will have a Lagrangian that contains the kinetic term for my U1 gauge fields, let's say my photons. We are going to have then a scalar field with now a kinetic term that also contains the interactions and some potential for my scalar field, a complex scalar field. Okay, where now this derivative mu, remember, is this, the covariant derivatives is the normal derivative minus the interaction of the gauge bosons. And this is something that is necessary in order to have an invariance of, x mu, an invariance that is local, so a gauge symmetry. Okay, so like yesterday we were talking about Ferners, you can also think on scalar field that is invariant under a local symmetry. The simplest one is U1. It's just a phase. It doesn't have any structure, matrix or vector structure. So let's just do this one. That is called the scalar QED. So once you impose this, you realize that you need to promote the derivative to a covariant derivative. So you need to introduce new degrees of freedom, these photons that have exactly this propagator, and so on. And notice that in this propagator, there is no, of course, no type of mass or anything. At that level, we have a scalar field with a potential, some mass, some interactions, and we have massless photons. So let's, as before, assume that the potential of this complex scalar only depends on the absolute value and is the same as before. That's all. I don't know what I'm doing. Yes, lambda phi to the fourth. Okay, so this part is exactly the same as before. We have a scalar field with exactly the same kind of potential that is going to have this non-trivial structure. So the description of now let's find the vacuum is going to be exactly the same. We find that there is no trivial vacuum if m squared is negative, right? And as before, what we are going to do is to redefine and say that this is going to be some shift plus real scalars. Okay, so we do exactly the same. But now this field is charged, or it couples to this photon. So what happens to the photon because now the scalar has a non-trivial structure? Is anything going on with it? So we can evaluate each of these terms. For example, derivative 5 will now have something that has this covariant derivative, and then this b plus h plus I chi. So now we will have interaction between the photons and this new reparametrization of scalar fields h and chi. So for example, in the kinetic term of the field, we are going to get the following terms. Let me just write them down. We get the kinetic term for the Higgs, for the scalar. We can get the normal kinetic term as well for the imaginary part. Then we get an additional term that goes like this: v plus h squared plus chi squared, and this kind of terms. Okay. And the potential part changes as before. So at that level, we will have a massless sky and a massive edge. All right, so this has changed a tiny bit the situation, right? Now we have the kinetic terms we had before. We have something in this term over here that is this famous mass term, something that if I collect the terms gives me a nicely looking mass term for my photon. So this term that appear because I did this field reparametrization that I need to do because now I'm in a non-trivial vacuum also generates at low energies spontaneously something, a term in my Lagrangian that is a mass term. So though I started with a theory that is U1 invariant, gauge invariant, where my photon is massless, apparently, once I consider the non-trivial structure of my vacuum, my photon is going to start changing and have a mass term. So when it propagates in that vacuum, it's going to appear as a massive photon. But the story didn't, and this mass is going to be related to how much the photon couples to the scalar field and how deep you want, or the parameters of my theory. But the story doesn't end up there. So now we go from a massless photon to something that looks like a massive photon, a massive gauge boson. And there is like a mismatch in the numbers of degrees of freedom. As you know, a massless photon contains 2 degrees of freedom, the 2 transverse components, whereas a massive vector, in this case, contains 3 degrees of freedom. So 3 functions that describe this photon. Right now, I've done this change in coordinates. Something shows up that looks as if a mass for the photon, but it's not like at this stage. I know that a massive photon requires 1 additional degree of freedom, 1 additional function to actually describe its dynamics. So where is this degree of freedom? And the degree of freedom is going to appear over here. Those terms will be responsible for that. I'm going to tell you this in just a few minutes. So we get these additional terms that look as something like this. Right? And this, if you try to interpret this term, well, let's say minus E times V, this term, is like as if I had a photon that suddenly transforms into a scalar, this massless scalar. Again, as in the case of the tadpole, if you have a Lagrangian where the kinetic term of your fields is mixed with another guy, so this is a mixed kinetic term, all what this is telling you is that your description is not the correct one, that you have to diagonalize this and try to find out what is the correct degree of freedom. Because you want to have a canonically normalized set of degrees of freedom. You have your F mu nu for the gauge boson, and you want to have a decay, and you don't want any kind of kinetic mixing. You don't want, what it means is that if it appears, you have done some field parametrization, and such terms appear, some kinetic mixing, it's just an indication that to actually visualize and see the proper degrees of freedom, you need to do something. Okay, so what we are going to do is to use the U1 gauge invariance to actually redefine my A mu, because I know I can do A mu goes to a new photon with some d mu beta, right? And in principle, my U1 gauge invariance means that describing my photon this way or this way, I should get exactly the same. So I'm going to use this freedom I do have to get rid of this. to find another term after doing this reparameterization that exactly cancels this. And the way to cancel is simply assume that beta is my chi. So what this is doing, what this parameter or the parameterization now is doing, is now it's going to give me a Lagrangian that depends on my Higgs, that depends on my photon, that now has a mass term, and where the dependence on chi has disappeared. If I do this, if I redefine my photon to make sure this term disappears, so it's absorbed in this field reparameterization, any other term from this chi that appear in my Lagrangian disappears as well. If you want, sometimes this is mentioned as A mu has eaten up the chi degree of freedom. And by eaten up, meaning that now in the new Lagrangian, my photon is there and the chi is no longer there. And eating it up means that now I have 3 degrees of freedom. I have a massive photon. And this 3rd degree of freedom was precisely this additional function chi that I have introduced. And the way I introduce it is going to, if you want, quote unquote, a gauge where my beta is precisely this chi, this propagating degree of freedom I had at the beginning. So you see, the way the Higgs mechanism works, which is to provide a mass term for W's and Z's, is quite subtle because not enough that at some point you end up with a W plus W minus term over here. This is not good enough. You actually need to explain how this W plus W minus, which were 2 degrees of freedom at the beginning, become a massive gauge boson which has 3 degrees of freedom. And the way it happens is that in the Higgs mechanism, the Higgs contains a real part, let me call it the Higgs field, the Higgs particle, and it will contain another scalar field, G or chi, sometimes it's called G. When electroweak symmetry breaking happens, when you are considering the vacuum of your theory where the Higgs gets a BEV, this initial degree of freedom, so a complex field, ends up with a real particle, the Higgs, plus another degree of freedom that disappears from your theory because it ends up being eaten up, you want, by the W. So from the description at low energies, you no longer see 2 degrees of freedom for your Higgs. You actually see only one, that is the Higgs particle. And this second degree of freedom is in a rather subtle way being introduced into the gauge bosons to precisely match the degrees of freedom that you need to have. And I think I'm going to finish here. Really what I wanted you to see is that the Higgs mechanism is really putting together a lot of ideas. The idea is that if you generate this mass term for a gauge boson, it has to be an infrared pure term, something that is not affecting the ultraviolet structure, and that leads to this spontaneous symmetry breaking concept that is much broader than the Higgs mechanism, but also that when it comes to gauge bosons, this matching of degrees of freedom is highly non-trivial, and these Goldstone bosons, this chi is a Goldstone boson of the symmetry that disappears from the low energies. You don't see this massless guy anymore because it is incorporated into this gauge boson to become a massive. Sometimes then these Goldstone bosons are called would-be Goldstone bosons. They will be Goldstone bosons if they haven't been eaten by the W bosons. But we don't see them at low energies. Okay? Okay.
There are a couple of questions.
Yeah.
The first referred to the first line of this slide. Kinetic mixing violates energy momentum conservation. Does not the correct field parameterization?
So the kinetic mission, again, if you have a Lagrangian with kinetic mission, write it down. That's fine. You can write whatever you want. It's just that when you want to then think on chi propagating or a mu propagating, this term is not correct. So you need to go to a new chi tilde and a mu tilde where this term has disappeared. So it has a pure kinetic mission for chi and a mu. What I mean by propagating is you are going to do field theory. When I write this, when I do this wiggly thing, all what I'm saying is that I'm going to write a quantum field theory where I get p squared plus m squared here with some Lorentz structure. But I can only do this, I'm only allowed to assign a diagram in a propagating term like this to something that is canonically normalized, where the kinetic terms are the ones that they should be. So if in your Lagrangian you have a mixed kinetic term, no worries, just get rid of it. Find a new reparametrization where this disappears.
Okay, and another question. Can the scale separation of the neutrino mass from the other leptons be due to an approximate global symmetry?
The thing that the Goldstone theorem and the fact that with the Goldstone theorem we can think on very separated scales. For example, you could have, in the case of QCD, lambda QCD, and then you have the pions. This separation of scale, this gap that appears naturally and can be explained with the Goldstone theorem, is with guys that are scalars. Okay? So the neutrinos being fermions, you cannot play these games of thinking on them as pseudo-Gaussian bosons or anything. Those are scalar fields. Just to clarify this, but coming back to your question, so yes, you can use the spontaneous breaking of symmetries or the approximate symmetries to actually try to understand in general separations of scales. The whole, model building around the Higgs mechanism is precisely trying to understand this large hierarchy between the electroweak scale and the gravitational interactions. So supersymmetry, for example, tries to do these kind of things, try to explain why a light scalar sector is so much lighter than other scales that are up there. So neutrinos being fermion particles, you cannot apply directly these kind of lessons, but at least, again, you can marry these guys through supersymmetry to some scalar, and then you can do other types of games. Any more questions, Luca?
The last one, still regarding the kinetic mixings, the mixing about the kinetic terms. Does the mixing of the kinetic terms reappear at high energy because Goldstone boson will decouple from gauge fields?
Very good question. So we know that yes, indeed, our Lagrangian started with this mu and this scalar field, complex scalar field, no? That contains H and chi. And what we've done is realize that at low energies, if we want to account for this non-trivial structure, the vacuum, blah, 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 then we had to reparameterize things. And there is where we see the mass term acting. We see this Goldstone boson that is being eaten and so on. At high energies, we will indeed end up seeing the original Goldstone bosons. And this is something that, if you want at high energies, this breaking, this spontaneous breaking is no longer effective. That's why it's called spontaneous. So you have SU2 cross U1 in the standard model, and at low energies, the only remnant that you see of this symmetry is one electromagnetism. At high energies, this is the symmetry that is at play. So there is a restoration of symmetry at high energies. What did I want to say? I wanted to mention something. So one way of checking this, one way of seeing this restoration of energy is precisely through W scattering. So with W scattering, you might end up, producing the Higgs And you know that these massive W's at low energies have eaten the Goldstone bosons, but these Goldstone bosons actually form part of the Higgs doublet, no? These complex scalars. So there are consequences of this larger structure, of this restoration of symmetry at high energies, for example, in WW scattering. If you look at the Peskin Schroeder, there is a good discussion about this, about the WW scattering also. Also to mention, since nowadays there is a lot of interest in the Large Hadron Collider, in particular, like the hot topic or the horizon regarding the Higgs is to precisely do double Higgs production. They want to see this process where quarks and gluons of the proton produces two Higgses. Why do they want to see these two Higgses? Because all these two Higgs production will precisely be probing this kind of scattering, will be precisely probing whether really there is this restoration of SU2 cross U1. So it's really probing the potential of the Higgs and the deeper structure of electroweak symmetry making.
Okay, I don't think that there are any other questions. At least nobody is writing. So I think we can close here. So thanks again, Veronica, for these next lectures. It has been a pleasure to have you here.
Thank
And
you.
hope the next time we will be by presence.
That would be nice. Okay. And again, if you have any questions, guys, you can send them by email and I'll do my best to answer. Okay. Good luck. Bye
Thanks,
bye.
Veronica. Bye.
Adios.
So everybody, we will close here the first theoretical lectures on standard model. Tomorrow there will be the tutoring lectures. And next week it will start on Tuesday, not on Monday. It will be the time for flavor and effective field theories. So see you tomorrow, still at 10 a.m.